Graphing log functions. So just recall that the inverse relationship between exponential and log functions is also useful for graphing log functions. We'll be graphing log functions by graphing the parent, then performing the transformations. Everybody should be familiar with the transformations at this point. It's shifting left, right, up, down, and reflecting, stretching, shrinking in the coordinate plane. So one thing to be mindful of, just like with exponentials, is that the parent function can change. Here you see the general form. The general form is y equals log base b of x minus h plus k. So for this, you have y equals log base b of x, and that is your parent function. So it's going to be specific to the problem. It can change. You also need to eliminate all those other values. If we look at the first example set, the directions say to identify the parent function and the inverse of the parent function. We learned about inverses last class. Here we see we have y is equal to log base 7 of x plus 2. The parent function is just log base 7 of x. And then we're looking to find the inverse of the parent function. So finding the inverse of the parent function is when you switch your x and y variable and you solve for y. Solving for y requires you to convert to exponential form. So if we do this off to the side here, we have y is equal to log base 7 of x. I'm going to start by switching x and y. The actual directions tell us to isolate the log, the base, and the argument, which we already have here, and then convert to exponential form, which is when you either do the loop method or memorize the order. But either way, you're going to convert to y equals 7 to the power of x. This is the inverse of the parent function. So y is equal to 7 to the power of x, and it's found by this process here. We did it, I believe, last lesson. Number 2, y is equal to log base 4 of x minus 1. Log base 4 of x is your parent graph. If we convert this to the inverse, you guys can do out the work if you need to. If you can at this point see what the inverse is going to be, that's great. It's going to be y is equal to 4 to the power of x. Number 3, y is equal to log base 2 of x plus 3 and then minus 2. The parent graph is y equals log base 2 of x. The inverse of this is y equals log base 2. I'm sorry. The inverse is y equals 2 to the power of x. Number 4, y is equal to log base 1/3 of x plus 4. The parent is y equals log base 1/3 of x. The inverse is y equals 1/3 of x. All right, so steps to graphing a log function. I'm going to add a couple notes to this just to help us when we go through our examples. The first step is to identify the parent function, which is what we just did above. The second step is to identify the inverse of the parent function, and here's what I'm going to add. You need to make a table of values of the inverse as if you were going to graph the inverse. So make a table of values as if you were going to graph it. The third step says to reverse the x and y coordinates of the inverse. So that means you're switching everything. You're switching your x and y coordinates, you're switching your domain and range, you're switching the asymptote. You're reversing all x and y coordinates. And then the fourth step is to graph the log function and perform any indicated transformations. All right, general form, we already talked about that. It's important to know that now we have a vertical asymptote. Previously, we graphed exponentials where we had a horizontal asymptote, but now we have a vertical asymptote, and the vertical asymptote is always going to be equal to your h value. So it actually starts at 0, and then it shifts left or right with the graph. All right, your horizontal shift, as it has been all year, is directly with the variable in the parentheses. If it's x minus h, it's shifting to the right. If it's x plus h, you're shifting to the left. And your vertical shift is your k value. That's if you're shifting up or down. So if you're shifting up, that means you're adding k, and subtracting k tells us to shift down. Those are the only two transformations we're going to do for logs. I know there are more transformations. You will see those in later math classes, but we are just talking about the general idea of logarithms. So we're just touching touching base on a few different things, but we're not going into depth with logarithms. So if we take a look at the first example, we're graphing log base 2 of x. And I'm going to go through every step for the first one. I'm not going to do that for all of them, but for this one, just so we can see the whole graph, we're going to start by identifying the parent function. That's step 1. In this case, we don't even have to change anything. The parent is the graph that's given to you. Y is equal to log base 2 of x. Step 2 is to find the inverse and to make a table of values. The inverse is y equals 2 to the power of x. So I'm going to make the table of values for the exponential function, which we've already graphed. So hopefully you remember when we were graphing exponentials, we tested values -2, -1, 0, 1, and 2. 2 to the power of -2 was 1/4. 2 to the power of -1 was 1/2. 2 to the power of 0 is 1. 2 to the power of 1 is 2. And 2 to the power of 2 is 4. So just for explaining purposes, I'm going to graph this. I'm going to graph it in light gray, just so I can talk about the answer. Typically, you would not graph this, so you don't need to do this on your paper. I'm graphing this function just to explain to you where the log graph comes from. So also in gray, I'm going to highlight that we have a horizontal asymptote for this graph, and the horizontal asymptote is located at y equals 0. If you recall, we also have a few key features. The domain is negative to positive infinity, and the range always corresponds with the horizontal asymptote, which is from 0 to positive infinity. All right, that takes care of step 2. Step 3 is to switch everything. So you're switching your x and y coordinates. That means I'm going to make a new table of values. And right here, this point, instead of the x value being -2 and the y value being 1/4, you're switching these. You're going to have an x value of 1/4, a y value of -2. The next point, switch those, x value of 1/2, y value of -1. Next, x value of 1, y value of 0. x value of 2, y value of 1. X value of 4, y value of 2. So we switched. And now in step 3, I'm going to graph this graph. I'm going to graph these points, the ones that I just switched, and I'm going to graph those in pink because these are actually our answer. So 1/4 -2, 1/2 -1, 1 0, 2 1, 4 2. Now this graph has a vertical asymptote. So not only did the points change, but now everything changed. So what was previously called our horizontal asymptote at y equals 0 is switching. It's now going to be called the vertical asymptote. And instead of being at y equals 0, it's at x equals 0. Again, everything switches. When I say everything switches, switch your domain and range. If we look at this graph, the domain is restricted. That graph never goes beyond 0. It does head towards positive infinity. The range looks like this graph goes up and down forever, so it's from negative to positive infinity. So this purple graph, or the pink that I'm highlighting in purple, is your final answer, and these highlighted purple parts are your final key values. The gray graph is actually not part of your answer at all. I just used that to show you how everything switches. Okay, you use the inverse function to switch and then graph your final answer. If we move on to number 2, we have log base 3 of x. In this graph, your parent function is y equals log base 2 of x. And the inverse is y equals 2 to the power of x. So it's actually the graph we just did. But if I make a table of values, I have -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. And then I'm going to switch these points for my parent function. So I'm not actually going to graph these. I'm just using these to switch them. My new table of values, when I switch these points, is going to be at 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2. And now I'm going to graph these. -1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2. Here's your parent graph. Okay, but wait, we're not done yet, because this graph actually indicates that we're shifting to the right 1 unit. Oh, I said that wrong. We're actually shifting up 1 unit. There's no parentheses. So shift up 1 unit. That means every point shifts up 1 unit. Shifting this graph up 1 unit does not change the horizontal asymptote. The horizontal asymptote is still going to be located at x equals 0. Oh, and I said that backwards too. It's actually the vertical asymptote. It's still at x equals 0. I just gave it the wrong name. Vertical asymptote is at x equals 0. The domain is from 0 to positive infinity, and the range is from negative infinity to positive infinity. Okay, here's your key values. The vertical asymptote only changes if you're shifting left or right on the graph. And that leads us to number 3, where we are shifting the graph to the right 3 units. So number 3 is the first one that our vertical asymptote will change. Number 3 has the same parent function. The graph is y equals log base 2 of x minus 3, and the parent graph is just log base 2 of x. So that tells us that the inverse is y equals 2 to the power of x. Now, just to save us some time in the video, I'm going to just copy my table of values, which I found in number 2, and I'm bringing these over here for number 3. Actually, you know what? I don't even think I need this. We already found these values, so we're using the same ones that we found in number 2. I'm going to go ahead and graph my parent function at 1/4 -2, 1/2 -1, 1 0, 2 1, 4 2. All right, and this is indicating to shift the graph to the right 3 units. So I take every point on my graph and I shift it right 3. Originally, our vertical asymptote was at x equals 0, but because we're shifting right 3 units, we also shift this right 3 units. So now our new vertical asymptote is at x equals +3. The domain always matches that, so it's from 3 to +infinity, because you can see this graph approaches that line, but it never actually touches or crosses. So 3 to +infinity, and the range is negative to +infinity as the graph goes up or down forever. Okay, why don't you do number 4 and 5 on your own, and actually at the end of class when I go live, I'll do number 4 and 5 if you have any questions on them. My answer key is posted to the website if you would like to see them. I'll just give you a quick hint. Number 4 is the same parent function, log base 2 of x, but number 5 is the first one that's different. It's y is equal to log base 4 of x. So make sure you pay close attention to the parent function and then to the transformations.